product is the one where the hydrogen that's added goes onto the carbon that already started with more. Okay? That's the addition reaction. This was in the reading assignment. Now, where I went from here, we talked the day before about alcohols, ketones, and aldehydes. So we covered those two. And how are we doing for time? I have one other type of reaction that I'd like to go through with you. I don't think that anybody in here studied oxidation reduction in Chem 1. Does oxidation reduction chemistry ring a bell to anybody? Redox? Who did you have for Chem 1, Claire? I didn't remember if anybody... I know I didn't. If you had me, a couple of you had me for Chem 1. We didn't do it last year. We didn't get through acids and bases, which was a shame. We'll spend a lot of time on acids and bases in this class. Why are you looking at me like that? Anyway, when we do inorganic chemistry, it's got a definition of of oxidation reduction that doesn't look like this. But in organic chemistry, we think of oxidation as either the gain of oxygen, which is a good reason for using the word oxidation. It's the gain of oxygen. But also, if a carbon loses hydrogen, that also would be considered oxidation. And there's a reason I'm telling you this. The compounds that we've learned now the other day, alcohols, ketones, aldehydes, all of those will participate in oxidation reactions. And we have to know both how they're made and what they become. So there's patterns to it. And let's go through what the patterns are. We talked about what an aldehyde is. It's where you have a chain of carbons. The end carbon has a double bonded O on it. Aldehydes are made by taking a primary alcohol and having it undergo oxidation. Now I'm writing actually behind the TV, so some of you can't even see what I'm writing. But a primary alcohol is one in which the OH is attached to a carbon, which is only attached to one other carbon. It would be like the OH is on the end carbon in the molecule. That's a primary alcohol. In a secondary alcohol, the OH is kind of in the middle somewhere, like a ketone would be. The attaching carbon is attached to two other carbons. That's secondary. A tertiary alcohol, if this is possible, you're going to have, and I'm just making these squiggly lines like, okay, the rest of the parent is we don't know where the molecule ends. But somewhere in the molecule, you're going to have a carbon that has three other carbons on it. That would be a tertiary. So the attaching carbon on the OH is attached to three other carbons, a tertiary alcohol.
Is this like similar to like the tert-butyl or?
Yes.
Okay.
This, just that without any other lines, and that would be CH3 and that would be CH3. That's tert-butyl alcohol, T-butyl alcohol. Yeah, where have you learned that or heard of that before, Jane?
What? Oh no, it was in the reading, but you told us to skip it.
Oh, tert-butyl, yeah, okay.
But then you just told us to memorize them. You don't memorize them.
Those are the ones, yeah.
Yeah.
It sounds like you've learned
No,
them.
I didn't memorize. I just
Okay,
know the
just
structure.
remember T-butyl, okay.
I just know the structure. I don't know that.
Sorry about that, Carol. That wasn't very nice of me to do. Put that behind so you guys couldn't see it.
Oh yeah, wait, what does it say behind?
Over here?
Yeah.
Secondary is CH2. What you need to know is a secondary alcohol, the attaching carbon, has a carbon on its left and on its right. A tertiary carbon, you got the attaching carbon on the OH, has one on the left, right, and above. So it's attached to three other carbons. I won't do that again. I'm sorry that I put that like that. We couldn't see it. So now going back, just that was all to define one of the words in this process. To make an aldehyde, you need to start with a primary alcohol, where you have the end carbon has an OH on it. And what happened? And I'm not going to be telling you the whole story about this oxidation. We also will spend a lot of time in here talking about oxidation reactions. Not so much in organic chemistry, but in the inorganic part of the course. Oops. Well, I'll just leave it like. No, I would rather. It's not like I'm trying to hide anything from you, but I'd like to just focus on one part at a time. So let's take a look at this reaction. Here's our primary alcohol. The OH is on one of the end carbons. What I'm not showing you here, this doesn't just happen. The way the chemical equation is set up, it looks like this just becomes that, and away we go, and there's never any of that left. That's not true at all. This is, what's the name of this? Propanol. Not just propanol. Got to say where the OH is. One propanol. Right, because it could be, the OH could be there on the second one. This is one propanol. One propanol is a very stable compound. We have a bottle of it in the back room, in our stock room, and it's been sitting there for years. It doesn't just change into this suddenly. What I'm not showing you on here is this reaction only happens if this, you stinking thing, if the propanol is mixed in with something called an oxidizing agent. An oxidizing agent. That's not shown on this. And there's, I guess, a good reason I'm not showing the oxidizing agent. If I went through what exactly this reaction goes to, it would take way too long. It's a complicated process. The process of a reaction is called its mechanism. So the mechanism when you have an oxidation is messier than we want to deal with right now. So I'm just leaving it out. Not that I'm trying to pretend it's not there, because I'll tell you, hey, this has to be in the presence of an oxidizing agent. I'm just not going to go through how it happened. I will tell you this. Common oxidizing agents, there's two very common ones in chemistry. And you'd recognize the formula. Those are ionic compounds, potassium permanganate. And the other very common one is sodium or potassium, I'll just use sodium here, dichromate. Potassium permanganate, sodium dichromate. What do those two look like they have in common?
They both have the polyatomic.
They're polyatomic ions. What else? Lots of oxygens. These are very good at supplying oxygen to other things to oxidize with. So that's why we would call them oxidizing agents. And they're very good at it. We'll use them. We'll do labs that have those and the whole thing. I love potassium permanganate. It looks like grape juice. It's a beautiful purple colored. What's that? Oh man, yeah, you're going to oxidize your mouth if you do that, and that probably wouldn't have a good ending. So let's not. I understand. They told me at the end of the year, I had a student last year, he's now a senior, Abhishek Koka.
Oh, yeah.
At the end of the year, he told me he tasted everything that we did in every lab. Oh my God.
Wait, but isn't that really unsafe?
Really unsafe.
Like what? But that's like going.
And he's alive, yes. I saw him at the beginning of the year. So he lived. And I don't know, maybe that was an exaggeration. I don't know if he tasted everything, but like there are other students that said he tasted the sodium hydroxide that we use. I would never put that stuff in my mouth, ever. He said it was kind of salty. You know, there you have it. So, and I don't say that so you become curious and want to do it too. I don't want you to do that. But anyway, that was a total diversion. I'm sorry about that. Here I don't even have that much time. I want you to see, in this oxidation process, there is no oxygen that this thing has gained. So even though I've told you that these are oxidizing agents and they're good for supplying oxygen, this has not gained an oxygen. It started with one and it ends with one. What happens in this reaction is this hydrogen and one of those hydrogens are removed in a fairly complicated process. And what happens is, here they are right there as a hydrogen molecule. both the oxygen and the carbon have lost something they're bonded to. The carbon was bonded to that hydrogen. The oxygen was bonded to that hydrogen. Those are gone. So now the carbon and the oxygen can make another bond, and that's what happens right there. Is there already was a single bond, a second bond is made between the carbon and the oxygen. That is the production of an aldehyde. You have to start with an alcohol. This thing has to start with the oxygen there. And rather than having one bond between the C and the O, now two bonds are there between the C and the O, and that makes it an aldehyde. So that's what I need you to know, is that an aldehyde is made by taking a primary alcohol. Remember, for an aldehyde, the C double bond O has to be on the end. So we start with a primary alcohol, oxidize it, two hydrogens go away, and then a double bond is made. Now, the aldehyde can continue to oxidize. If we had a strong enough oxidizing agent, not only would it take the alcohol to an aldehyde, it would continue taking an aldehyde to another higher oxidation state. That would be called a carboxylic acid. I'll go ahead and expose the name of this thing. So this would be now called propanal. Remember, aldehydes end with Al. Propanal can continue to oxidize, and there's going to have to be some water present because the water is going to break apart and get kind of taken advantage of. I'll just let you go ahead and write that down, and then I'll highlight part of it.
Wait, so for aldehydes, do they always have to be dehydrogenation like equations? Because you know how it's going from like saturated to unsaturated with like the double bond.
Mm-hmm.
Is it always like that, or like because you said you have to start with a primary?
Yes, and
So
everything you just said is true.
It can never have like a double bond in the beginning of like the reactants.
Right.
For
It
all
will. Yeah.
compounds. Okay.
Yep.
So, like under the aldehyde little segment, the resulting compound, that's one propanal.
Yeah, you don't even need to use the one though, because for an aldehyde, it has to be on the end carbon. So that C double bond O, yeah, you don't need to specify where it is because it has to be on the end. You just call it propanal. Yep. In this second oxidation now, this hydrogen and one of those hydrogens, one of the two hydrogens, get removed, and there's our hydrogen molecule. Now there's still one hydrogen there on the oxygen. That OH is going to replace where that H was. That's what that part's doing right there. So the C double bond O stays put. It doesn't do anything. But that H gets replaced with an OH. So this thing has gained an oxygen overall. It had an H already. It gains another H. But so there's no net change in the H's. But it did gain oxygen. So that's what makes that part an oxidation. All organic acids are carboxylic acids, and all carboxylic acids will have that on the end of the molecule. A C double bond O and a single bond OH. And just with this example, you can see how they're named. You drop the al from the aldehyde and you use oic acid for its name, propanoic acid. So we've got 3 carbons in the parent. There's our pro, and propanoic acid is the end. Okay? Just got one other slide, and that's about how ketones are made. You got one more slide in you? You all right? Here's the end of the day, and I'm going right up to 209. You can make a ketone by oxidizing a secondary alcohol. Secondary alcohol means there's going to be an OH somewhere in the middle of the chain, like that. There's your connecting carbon. It's attached to 2 other carbons. That's a secondary alcohol. Oxidize that, and you get a ketone. In the same exact mechanism that the aldehyde was made.